And welcome to SanfordFlipMath. We are doing AP Calculus. We're going to run through some examples from Calculus by Finney, Demana, Waits, Kennedy. And we are working on actually from section 4.4, which is about optimization. And we're working mainly from page 227. And this is number 11. And so we're basically trying to build a tank that will hold 500 cubic feet of stuff. It's supposed to have a square base and an open top, a rectangular shaped. And again, the idea is this is like X, and I don't know what the height is, but there it is. And ultimately, we need it to hold 500 cubic feet. And just a reminder that the volume of a prism like this would just be length times width times height. And so in this case, we want that to be equal to 500, and it's x times h. And then the rest of this is how in the world are we going to minimize the weight? Because that's the goal. And that question B about this is about minimizing weight. And so I guess my question then is, how do we actually make that happen? All right, so the issue here is we're trying to make the tank weigh as little as it possibly can, and that means that the substance, the metal it's made out of, needs to be minimized. Now, we're going to make an assumption that the thickness of this metal everywhere is going to be the same. And so if we make that assumption, then ultimately what it's about is about the surface area of the tank. And so I'm going to do a little, some people call this a net of what it is, and the idea is that here's the base, and then I would fold these sides up and make that box. Okay, so this is X all the way around, and then the sides, this would be that height. Okay, so now again, I want area of this thing. Now, each one of these rectangles is x by h in terms of area. There are 4 of them, right? There's 1, 2, 3, 4 of these guys. So if I'm talking about area, I'm going to add up those 4 sides, 4 times x times h, 4 of those x by h rectangles, plus I have an x times x square in the middle. So this total area that I'm going to minimize is just 4xh plus x squared. Okay, so that's what I want to minimize. Okay, so we have a formula, an equation that we want to minimize. But the problem is that I have too many variables. I need to get the h out of here. So let's go back to the volume for a second. This was 500 equals x squared h, and if I could divide both of these by x squared, then I have a way to make h equal 500 over x squared. Okay, so let me rewrite this. This is going to be area equals 4x times 500 over x squared plus x squared, and again, this is just the h. Okay, so at this point we want to minimize area, and I have an equation that I can work with. I'm going to clean this up a little bit. This x will divide out of the numerator and the denominator. Okay, so this is now really 2,000 over x plus x squared. I'm going to write it one more time, and then we'll start actually doing derivative. So this is 2,000 x to the negative 1 plus x squared. Okay, so just a reminder that we are trying to find a maximum or a minimum here. So what we're looking for is endpoints of the interval, if there are such a thing, any place, and then critical points. And remember, any critical points are places where the derivative equals 0 or the derivative does not exist. Well, the only endpoints really on this would be if we had a dimension equaling 0, which is kind of goofy, so that we need to not include that. And then the derivative doesn't exist where the function is not continuous, and it's not continuous at 0 because we'd be dividing by 0, but also it doesn't make sense anyway, so that's really not a big deal. So our only critical points are really going to be, our only interesting critical points are really going to be where the derivative is 0. So let's start finding derivative. Okay, so -1 times 2,000, x to the -2, plus derivative of x squared is 2x. We want to make this whole thing equal 0. And I think most people are more comfortable with working with that in that form. And so we just need to solve this. Okay, so I think what we'll do, I'm going to multiply both sides by x squared. Oh, yeah. So I'm going to multiply both sides by x squared so I can clear the denominator, sorry. X squared and this x squared, that's just going to cancel out. So -2,000 equals x squared times 2x is 2x, sorry, not equals, plus 2x cubed, and 0 times x squared is 0. I'm distributing x squared times 2x, so 2x to the third. I'm going to add 2,000 to both sides. Divide both sides by 2. X equals, looks like 10 to me. Okay, so we know the value of x that'll make this a minimum or a maximum. I'm going to wager a guess that this is going to be a minimum, since that's the only critical point. We could find out whether that truly is a minimum by either playing with derivative or looking at specific values of the area, but I'm just going to roll with it at this point. Okay, the question asked for dimensions. Well, we just found x is 10, and just a reminder that this box was x by h. Okay, so I already know it's going to be 10 by 10 by something, so I guess I need the h. I need the h. Well, I have a cute little formula over here that says, I never really wrote it, h equals, but it's 500 over x squared. So, yeah, this is getting a little messy. How about I just come over here? Okay, so h equals 500 over x squared, so 500 over 10 squared, which is 5. So it's 10 by 10 by 5, and the units for this whole thing were originally cubic feet, so this is feet. Okay, and it's assumed, so it's not really x equals anymore. Goodbye. And we are done with that bad boy. Now, again, part B asked about how did this deal with weight? And remember that weight had to do, we assumed there was uniform density of the metal and uniform thickness of the metal, so we could basically ignore the thickness. If we minimize the area, we minimize the amount of metal involved, and so that minimizes the weight. Okay? All right, so popping back around, we're going to talk about the issue of whether it was truly a maximum or a minimum. So the question is, at x equals 10, how do I actually know it was a maximum or a minimum? Well, I know because the slope there was 0. That's what we found as a critical point here. I don't know what it was. All I know is the slope was 0. So it could have been a maximum, it could have been a minimum. Okay? But if I do the second derivative, that's what this is, second derivative, at that point, since this is, second derivative is positive, that tells me that this was concave up, which tells me it had to be this, which makes it a minimum. Okay, so the second derivative test, this is going back to section 4.3. Yeah, I'll go with that one. Section 4.3. The first derivative test said that maximums or minimums are at critical points or at endpoints. So find this first derivative, set it equal to 0. Second derivative test said if you're at a critical point and the second derivative is positive, concave up, then it would actually have to be a minimum. If you are at a critical point and the second derivative was negative, concave down, then it would have to be a maximum. Okay, so it truly was a minimum. Okay, we are talking about number 21, which is asking us to maximize the area for rectangle inscribed under the arch of the arch given by this lovely equation. And I'm just going to do a speedy little sketch of this. Just a reminder that period is 2 pi over b. So 2 pi divided by a half in this case is going to be 4 pi. The amplitude is 4. So I'm not going to do everything with this sketch. I just want you to see just a quick idea of what this looks like. And so here we are. If that's 4 pi, this is 2 pi, and this is pi. And if we continue this, here's our negative pi. And so this is that arch that they're talking about. Okay, so let me just kind of redraw that focused on just that part of the graph. And I suppose you could make this happen on a calculator, but there it is. And the idea is if we inscribe a rectangle here, now it could be that rectangle, maybe it'd be a taller rectangle, or maybe an even wider rectangle. But again, the idea is that it would be limited by that arch. Okay, so let me go back just to the green one. Okay, now a couple little issues here. This point, I'm going to call it cleverly x and y. And if that's x, then this distance is the x, and this distance is x. And so that base then would be 2x. Okay, so this height here, this y value, is also given by 4 times the cosine of 0.5x. So the area of this box is really going to be base times height, which I'm going to call 2x, times y, which I'm going to call 2x times 4 cosine of 0.5x. So I'm going to clean this up a little bit. 8x cosine of 0.5x. Okay, so if I'm going to maximize this, I'm going to do the critical point. Now, this is a product. So I'm going to do cosine of 0.5x times the derivative of u plus u, not 8u. Oh, dude, that was great. Let's try that again. So 8x times derivative of cosine is negative sine 0.5x times 0.5. Okay, so this is 8 cosine 0.5x minus 4x sine 0.5x. And I would like that to equal 0. So this is going to be 8 cosine 0.5x equals 4x sine 0.5x. Maybe I didn't want to do it that way. I don't know if I wanted it to do it that way. I don't like that. Okay, so this looks the same. And I'm going to factor out. No, there's nothing to factor out. I don't know. What do I want to do to solve this? All right, so this is not a trivial little equation to solve. I'm going to go ahead and divide both sides by cosine. And so when I do that, yeah, you're not going to like me if I do that all at once. So 8 equals 4x tangent of 0.5x. I don't like this. That's divided by 4. I'll do that just to clean it up a little bit. Yeah, what do we do with that? I don't know. Doesn't say. And let me just say this equation is ugly to solve, and the way that the book does it is they actually solve this graphically. So they actually type in y equals this, and or something similar to that, find the zeros of it, and it happens to be the one that works between 0 and pi is that, which gives us a width of twice that, and the height you can get by just plugging that into the equation. I know that seems like a sellout on this, and it's just the equation for this one happened to be a little extra ugly. Okay, that's it for this one. Thanks, guys. Bye.